Okay. So now uh, we are entering into the week 5. So we are entering into week 5. Okay. So basically, this week 5 is about PID controllers. Okay. PID controllers. So what I'll do is, Professor has explained in his videos extensively, starting with the basics of what is the purpose of the controller, um, through P controller, I controller, derivative controller, and combinations like PI, PD, PID controllers. So in all the 4 videos, so what I'll explain here in this live is I'll explain the first lecture clearly. Okay. So the basic difference between the open loop and closed loop controller in view of this control systems, in view of these uh, 4 concepts. Okay. Then I'll explain through derivations. Okay, how we will design this P controller. Okay, so the entire derivation. Then you can easily do the derivations for the other controllers, or you can watch process videos. So I'm hoping that after this live, you will understand professor videos much better. Okay, so that's the intention. Okay, so here the main motivation is for the design of the control systems. Okay, so a design of controller for any systems is to handle these 4 problems. Okay, so the problem of uh, stability, tracking, regulation, and sensitivity. Okay, these are major 4 problems in any of the control course. Okay, so any of the control system problems deal with these 4 areas. Okay, stability, tracking, regulation, and sensitivity. Okay, so for these requirements. So here what we will do is we have basically during our first lectures, we have seen 2 concepts, open loop as well as the closed loop. So now we will see, considering this open loop and closed loop, so how what we can do with these 4 concepts. Okay, stability, tracking, regulation, and sensitivity. Okay, so what are these requirements in open loop setting, right? And are there any advantages they give with the closed loop setting? Okay, that is our goal to learn in this lecture. Okay, so now you see this. This is the basic open loop control, where we have this reference input. Okay, and we have this output, actual output. Okay, reference input and actual output. Okay, so this will be your plant or system. Okay. So by the way, this lecture is very important. Okay. In understanding the next level of controllers. If you get any doubt, you please ask me. Okay. So this is the plant or system, and this will be the controller. Okay. So the G represents the transfer function. We know already this. So G represents the transfer function. Okay. So in the previous weeks, we have learned that transfer function is the Laplace transform of output to the Laplace transform of the input under initial conditions 0. Okay. So here in the open loop structure, there is no feedback part. We already understood the concept of feedback. Okay. There is no feedback from output to the input. Okay. So this is not there. Okay. So while designing the controller, so we don't consider this feedback from output to the input. So in our regular life, we have plenty of examples. So like we have washing machines, traffic lights, conveyor belts, so electrical circuits, etc. So particularly these traffic lights. Okay, so we directly give a green signal of let's say 30 seconds. We don't check how many vehicles are there. Okay, whether it is 10 vehicles, 50 vehicles does not matter. Okay, we directly give 30 seconds of green, okay, in particular north direction. Okay, so we don't take feedback how many vehicles are there. If there are less vehicle, we should give less than 30 seconds, or if there are more vehicles, we should give more than 30 seconds. We don't check like that. Okay, the current existing system. This is one of the best example for open loop control. Okay, so now in the open loop control, the disadvantages are they are heavy prone to the disturbances. Okay, so they are largely affected by the system parameters. Okay, now if you see this open loop, the output equation. So here output equation, what we can do? So R of S we are giving as a input to the controller. Okay, here we get the control input. Okay, UI of T. Okay, control input. So then control input is given to the summation. So the D is the disturbance. Okay, so the disturbance enters here and changes this control input a bit. Okay, so that I'll say after change modification in whatever the way the disturbance does. So let's call that is as some U tilde. Okay, so after adding this disturbance, okay, now if you see here R of S multiplied with G of S, that will be UI of T. To that you are adding D of S. That entire thing you are giving as a input to the here. Okay, then multiplied with G of S, you get Y of S. That is the final output of this open loop system. Okay, so this is that equation. Okay, R of S multiplied G of S plus D of S multiplied G of S. So this is one term. Okay, so this is that term. Is this clear? Any queries? If you are having any queries, please ask me. Okay, that is the output output value YOL of S. Okay, now what is the error? So you wanted to give reference input as R of S. Okay, the output you got is YOL of S. Okay, the error is nothing but the difference between these two. So if you substitute them, this is your expression. Okay, that is your expression. Now, so as I said, we are more concerned with four things. So one is the stability. Okay, next is tracking. So another is regulation. Final one is sensitivity. Okay, so through this lecture, we also need to understand what are these, what are these definitions of these four things and how we handle them here in the both open loop as well as the closed loop. So first, let us start with tracking. So basically, tracking means you have some reference signal R of T. Okay, you have some reference signal R of T. Your output should track that signal. Means output should follow that signal. For example, here in this case, we are taking this thermal control system. Okay, it is a system which has this transfer function as G of S. Okay, so the transfer function is 1000 by S plus 1, 10S plus 1. Okay, that is our system. Okay, to that system, our goal here is to track this reference signal R of T. It means that the output of this system track this R of T. Okay, the R of T has this behavior. This behavior is it having a slope of 10 degrees per second for 30 seconds. After that, it is 300 degrees Celsius. Is this clear? Any queries? The R of T behavior, any queries? Any queries? Okay, now you can see here. So what is our main intention? You can see that R of T, the red line, the red curve. Okay, so the red curve having so 30 degree per Celsius. Okay, till 30 seconds. After that, the value is 300. That is R of T. Okay, now our output, we want our output to follow this R of T. Okay, in the closed loop system, what is the basic idea? The basic idea, let us say this transfer function. Okay, if I DC value is, if you see that the DC value is 1000. Okay, if you just simply apply the final value theorem, you will get final value as 1000. Okay, that we call it is as a DC gain. Okay, so now if you simply multiply that 1000 with 0.3, you'll get 300. That is the basic idea, correct? So if you do that, that is, so take the input of 0.3. Okay, apply to the system. Okay, so you will get the 300. Okay, then you can plot this time response. You will get this blue curve. So this is your y of t. Okay, so you could see here at any point of time, this would represent the error between the reference r of t and y of t. Okay, so if you plot that error, cumulatively, you can see this second image. Okay, so the error starts at 0. Okay, so it's keep increasing around at let's say 12 seconds. The error is 80. Okay, then it starts reducing. Okay, but at the end you'll have some more error. Okay, at the end you'll have some more error. Okay, so this is the tracking means. The tracking basically defines that. Okay, so you have some reference signal r of t. Okay, your output must follow that reference signal r of t. So what you understand here is you have lot of error. Okay, the tracking error appears at any point of time. Okay, so particularly at the end you have this much error. Is this clear? Any doubt? Any doubt in this?
Will error be always there?
Sorry, that's the main question. Here in this setting, when we take the open loop, okay, we got some error. Okay, so now we have to see the same problem in closed loop setting, because what right now we are considering the open loop without feedback. Okay, yeah,
Yeah.
so that is with the tracking problem. Okay, next. So the regulation problem. Regulation means simply, so previously our R of t is the time varying function. Okay, now R of t will not be a time varying function, it will be a constant. Okay, now here you see, so in this, the blue curve, okay, blue curve is the constant value. Sorry, the blue curve is the constant value of 1. Okay, the red curve is our y of t. Red curve is our y of t. Okay, what did you see here now? So the regulation can be defined as now. Okay, so the ability of the system to maintain this constant output value of 1. Clear? So that value is always constant. We say that. So the regulated value of the system is 1. Is this clear? So the difference between tracking and regulation. Basically tracking is, so to track the reference r of t, which is the time varying function. Whereas regulation, it is the value is constant. R of t would be a constant value. Clear? Any queries? You can ask me. Okay, now suppose in this case, let us say, okay, so we are having, let us say in the first setting, we have this disturbance signal, D of S. Let us say the disturbance we are introducing is the step disturbance. Step disturbance, what is the Laplace transform? 1 by S. Okay, now let us see for this, what will be the regulation case. Okay, now here you can see, so here our intention is that our system has to regulate to 1. Okay, so our system, we wanted to make our system to regulated value of 300. Okay, here you can see the two things you can observe here. Okay, so the red one is the reference value r of t that we want our system to regulate to that value. Okay, here you should see the left image only. So this one is, okay, so output without disturbance. Output is without disturbance. Okay, so without disturbance, our system goes like this and follows like this. Okay, when we introduce the disturbance of this one, okay, our system started like this and it took a deviated value. Okay, so we are having an error here of this much at the final stage. Okay, now if you see the left side image, okay, this is with right side, left side image, you can see the tracking error. Okay. So initially the tracking error is very high because of this much, 300. Okay. So that is this level, initial value. Okay. Later, as our output y of t is getting closer to this r of t, okay, the error is getting reduced. Error is getting reduced. When there is no disturbance, error is zero. When there is the disturbance, so it came until here and it went like this. Okay. So the tracking error is non-zero. Is this clear? This is due to the disturbance. Okay. This is called as the regulation problem. Is this clear? Any queries? Ultimately, our output, we want our output to follow the reference value R of t, which is a constant value of 300. Okay. This is called as the regulation problem. These are the results with the open loop control. Okay. Now, next, stability. Okay. So in the third one is stability. Okay. So in the previous lives in week 3, we already introduced what is stability. So we found the two definitions for stability: BIBO stable and exponentially decaying stable. Correct. So we always talk. We are much interested in the exponentially decaying stable, which we uh, measure using the poles location. Am I correct? Am I correct? Right. So when we say system is stable, okay. So when we find the poles of the transfer function, okay, we say system is stable if all poles existing on the left hand side of S plane. Am I correct? So that is on the LHP. If any pole, if it is there in the RHP, okay, we say that system is unstable. Am I correct? Right. Now let us consider this image again. So without the disturbance, we have without disturbance. So we have this image, okay, where so the controller transfer function GC of S and the plant transfer function G of S, they both are connected in the cascade fashion. Okay. So then what is the overall transfer function? The overall transfer function is this. Okay. So now this would looks like so this format, correct? This would look like, so it will be having a numerator polynomial as well as the denominator polynomial. We know already that if we make denominator equal to 0, we get our roots. So those roots we call them as the poles. Am I correct? Those roots we call them as the poles. For example, you have G of S is this, GC of S is this. So the overall transfer function is this. In this, okay, so you can see this. So suppose what you can do is, suppose if A of S, so that is a polynomial, if its roots are positive values, if its roots are positive values, what does it mean? Okay, so what does it mean? The system is going to be unstable. Okay, what we can do is, now if you design your C of S in such a way that if your C of S and A of S is gets cancelled, okay, you can make your system stable. You can make your system stable, correct? So suitably designing D of S also. Okay. Similarly, the effect of the zeros also we can do the same thing. Okay, with the B of S and D of S expressions. Okay, with D of S and B of S expressions. Is this clear? So the stability behavior we can change by properly designing this D of S, okay, and C of S. That's my intention. That is the main point. Okay, by properly designing the C of S and D of S poles. Yes, it is. This is week 5. Okay, yeah. So the C of S by D of S is nothing but your controller transfer function. Controller transfer function. Clear? So that's how we can modify the stability of the system. This is the third aspect. Okay, fourth one is sensitivity. Okay, so the sensitivity is basically defined as, suppose we have a plant of transfer function. So G. Okay, So due to some changes in the frequency of the system, if transfer function changes to g plus delta z, with a small fractional change of delta z. Okay. Now what we do is, so percentage change in the gain is delta g by g. Okay. For open loop system, we have this transfer function. Okay. So let's call that is as L of S, which is the multiplication of GC and G. Okay. So when there is a change in the G, okay, there will be a change in L also, that we call as delta L. Okay. Substitute both L and delta L. You have this expression. Okay. You have this expression, that is the change in the overall transfer function. Okay. Now sensitivity, this particular term. Okay. So SGL. Okay. So sensitivity of the transfer function. Sensitivity of the transfer function L to changes in the plant G, that is defined as this way. Okay. Delta L by L divided by delta Z by G. This is how in this way you can calculate it. So you can define that is as fractional change in L defined as the fractional change in G. That is called as the sensitivity. Okay. So now you understand these four concepts. Tracking. Okay. So tracking. Yeah. Yes. Yes. Tracking, regulation, stability, and sensitivity. Okay. So if you choose any control system problem, so they majorly discuss or deal with these four concepts. Okay. So now we have seen these four concepts with respect to the open loop system. Okay. Now let us see the same aspects with respect to the closed loop system. Okay. So now what is the difference between previous open loop system and closed loop system? So we have added this part. We have added this part. Am I correct? Okay. So we have added this noise as well as this feedback part. Correct? So that is the difference. Okay. So what we call this is as the this part as the feeding the output to the input side. Okay. So basically what it does, it uses some sensor to measure the output Y and feed that output to the input. While measuring, you'll have some noise in the sensor. Yeah, uh, we will upload this in the live sessions, this video. Okay. So this video has, has been clearly explained by professor in the course lecture, but I am explaining it again for your better understanding. And if you have any doubts, you can ask me. Okay. Yeah. So we we keep some sensor to measure the output. Okay, and feed that output to the input. So since we are using some sensors, there will be noise in the sensor. So that's why we added this noise input also. The disturbance input is already there. Okay. Now we'll see those four concepts with this closed loop structure. Okay. Let us start with the tracking problem. Okay. First let us find out the error and output to transfer functions, etc. Okay. Now here, how many inputs we have? We have one input here, another input here, another input here. Three inputs. Okay. What we can do is to find the overall transfer function, okay, or overall output. Okay. So by using our superposition theorem. So what do you mean by superposition theorem? We use our additivity concept. Okay. In the superposition theorem, what we do? Okay, when there are multiple sources, input sources. Okay, so we switch off n minus one sources, and right, and we deal with only one source at a time. We find the output. So this process we will do for the all the sources. Then we add all the outputs together. Okay, so here in first case, what we do? We make d of s 0, n of s 0, and find y of s by r of s. Okay, we get this expression. Okay. The next case that will, this expression is that by CL of S divided by R of S. That is the transfer function. Okay. Next case, we make R of S 0, N of S 0. We get this expression. Third case, we make the other two terms 0, D of S and R of S. We get this expression. Okay. Using the simple block diagram reduction technique. So now this is the overall output. Uh, okay. Yeah, this is the overall output. So how do we got this? So we got this using the superposition theorem. Okay, using the superposition theorem. Clear? So now the control input. Okay, so control input we also find in the same way. This control input. Okay, control input. How do we find? So we have this. Okay, so control input is nothing but here we are getting this y of s. Okay, what is this one? This one is nothing but R of S minus Y of S. Okay, what is this U of S equivalent to? U of S is nothing but GC of S multiplied R of S minus Y of S. Okay, you can substitute that Y of S expression. Okay, so this expression into that equation. So you'll get your U of S expression in the same way. Okay, so once you have this, what is your tracking error? The tracking error is reference input minus the actual output. Okay, you get this expression once you substitute them. Now, so now let us see the individually. So what is this tracking error? Okay, so you will assume the noise and D of S goes to 0. Okay, so in this expression, so this term and this term goes to 0. You left with the first term. So that is this. Both other terms are zeros. Okay. So again, when you when there is a change in the plant transfer function, there will be change in the error also. So we call that is as delta E of S. Okay. So the delta E of S and add with the tracking error. You have this final expression. Okay. From there you can find delta E of S. Okay. So using this error now. Okay. So this we know already, this L of S. Okay. So you please write it, you will understand it. Okay. So finally, this is our expression for change in the error. Change in the error. So what it says, if L of S, that is nothing but the open loop transfer function. If it is large, okay. If it is large, so we get the small changes in the tracking error. We get the small changes in the tracking error. That is our final conclusion because L of S is in the denominator here. Okay. If plant transfer function is L of S is large values. Okay. So we get small changes in the tracking error that you can see with the same example. Okay. So we have the same transfer function. Okay. So the reference input is R of T, same reference input. Okay. So now this is our idea. Okay. So what we need to do is to minimize this error between the reference and the output signal. Okay. So with that should minimize this steady state error. Okay. That minimizes the steady state error. Let us say if we choose the GC of S is something like this. Some expression K1 plus K2 by S. Some expression. Okay. So to this expression and G of S is this. Okay. If we plot the results, you can see this. Okay. So again, the red one is same thing. R of T. Here red one. So it is varying with 30 degree per Celsius. Okay. Till 30 seconds. After that, it is 300. R of T is same. We are not changing it. Okay. So when we use GC of T as this expression, okay, and if we find the final output, you can see that blue curve. Okay. You can see that blue curve. Okay. So that is exactly following the reference input. The reference input. Okay. So at starting, you have some considerable error. So you can see this tracking error. You can see the tracking error. So initially you have the tracking errors, later reduced. Then somewhere here you have again this part of the tracking error. Okay, after this zone, so we have tracking error 0. So ultimately, what is the intention? So when we see the same case, okay, so in open loop control, we have tracking error. Final tracking error is of 10. Okay, let me show you that. Yeah, this one here. So here this value is 10. Okay, whereas now the tracking error is 0. Tracking error is 0. So this is all due to the feedback we have taken from output to the input. Okay, so that is all due to the feedback. Okay, that is tracking error example. So similarly, you can do the calculation for sensitivity. Okay, so you have this output we have already calculated previously. Okay, so this is the definition for sensitivity. Sensitivity of L with respect to the changes in the G, plant transfer function. Okay. So now in this, previously the L is nothing but open loop transfer function. That time we have L is equal to GC only. Now L should be closed loop transfer function because of this feedback also. So now this is your L, okay, which is nothing but GGC by 1 plus GGC for the closed loop transfer function. Okay. Now if there is a change in the G, there will be a change in L also. That change is nothing but delta L. Okay, if you substitute them, this is what you get. Okay, so we can talk about the sensitivity as, okay, sensitivity of L with respect to Z. This is your final expression. Okay, so whereas in the open loop system, this is what you have. Okay, in the closed loop system, this is what you have. 1 by 1 plus L, here G by L, delta L by delta Z. Okay, so we can compare both, right? So which is more sensitive to the errors. Okay, that is for closed loop system. Okay, next is stability. Stability is as usual. So you have this closed loop transfer function. What you can do is you'll find this y by r, which is nothing but GGC by 1 plus GGC H. Okay, this is the closed loop transfer function. Okay, so we find the same thing here and equate this part to 0 to find the poles. That part we call them as this. Okay, for taking H equal to 1. So the feedback gain as 1. Okay, suppose if you take G of S is this expression, GC is this. Okay, so the denominator is this. A of S, D of S plus B of S, C of S. Okay, here by properly choosing the expressions for C of S and D of S, okay, you can change the poles, you can change the roots of this equation. Okay, you can modify the roots of the equation. So choosing C of S and D of S is nothing but deciding the expression for the controller transfer function. Okay, so that is stable. It means that initially if your G of S, okay, yeah, B of S and A of S, if the poles locations are in the right hand side, so you can choose your C of S and D of S expression so that you will be choosing the GC of S, right? That changes the poles location. You can properly tune them to make the poles or push the poles to the left hand side. Okay, so that's the major point. Okay, so for example, if you see this, you have this G of X expression, okay, GC of S expression. Okay, so the characteristic equation is this. Okay, 1 plus GCG. So you can see this equation. Suppose if you take gamma is equal to 1, some constant. Okay, now see this entire equation. So here, if you know your delta value, so you can change the pole's location by changing the value of the k, by changing the value of the k. So where did that k comes from? The k is part of GC of S. K is part of the GC of S, which is nothing but which is nothing but the choosing of this C of S or D of S. Okay, so that is how you can change the stability of the system. Okay, so these are the four things. Then finally we have these two things. So how do we reject the disturbance, or how do we nullify the noise? Okay, so for example, in the same closed loop system, okay, make these two inputs to zero, noise and reference input. Make those two inputs to zero in the error equation, whatever we have previously. Okay, so in that error equation, so you can modify that to this level. Okay, so by keeping this g of s fixed, by varying this L of s. Okay, so because L of s is in the denominator. Okay, so if you keep on increasing the loop gain or loop transfer function L of s, okay, so the error can be reduced. This is what, this is error due to the disturbance. This is error due to the disturbance. Okay, so majorly these disturbances are created at lower frequencies. Noise will be created at the higher frequencies. Okay, so what we do here is you choose the loop gain at the lower frequencies, right? That will reduce the tracking errors or disturbance reductions. Okay, so in that way you can nullify the, you can reject the disturbances. Similarly, so you make the disturbance zero and reference input also zero. Okay, then you'll have only noise input. Okay, in that case, this is your expression, making other two terms are zero. Okay, so here also similar way. Okay, so here basically the noise signals are majorly generated at high frequency components. High frequency components. Here also basically you can tune your L of S, okay, to the lower values, because this is also in the denominator. So at higher frequencies, which will result in uh, reducing the noise components. Okay, so that is how you can handle the disturbance reduction and noise component in the closed loop system. Okay, finally, these are the advantages. So for both open loop as well as the closed loop, we saw these four things: stability, tracking, regulation, and sensitivity. Okay, what closed loop having advantages are, it improves the stability, or it gives the flexibility to tune the pole's location. Okay, similarly, uh, it handles the sensitivity well. Okay, it could reject the disturbances. Okay, so reduce the steady state errors. Okay, it can also do the noise attenuation. Okay, so it can increase the bandwidth of the system, the frequency band of the system. Okay, so only the disadvantages are, so we are reducing the gain of the system, which is the basic behavior of the plant. Also, since we have to do the we have to take the feedback, etc. All, okay, the complexity gets increases and cost also gets increases. Okay, these are the major comparisons between open loop and closed loop. Okay, clear? Uh, any queries in this? Anywhere? Any queries? So now what we will do is, so we will enter into the main concept of controller design. Okay, so let me go to those slides. We'll enter into the main concept of controller design. So I'll go little slowly. If you don't understand anything, you can ask me. I'll also share this PDF in the discourse. Okay. So now that we understand what is feedback control or closed loop control. Okay, so it can change the system response. Okay, without changing any of the system components. Okay, so you already have seen this open loop and closed loop structures. Okay, and you have seen the advantages of closed loop system and disadvantages also. Okay, so now we are entering into the concept of the main concept. So the objectives of feedback control. Why do you want to do this? Okay, so in the previous week 4 module, okay, so so week 4 module already introduced various terms like rise time, correct? Settling time. What are other terms it has introduced? Steady state error, correct? What are the other things? Overshoot. Am I correct? Is that right? Okay. So if you consider for first order system, okay. So if it is the, it's a second order system, so you'll have something like this, correct? Okay. So we define various terms like rise time. So this is the TR goes from 10% to 90%. Okay. Then this will be what? This will be overshoot. Okay. Then this will be settling time. Then this will be SSE. Okay. That is nothing but the steady state error. Clear? So there, these terms are defined for both first order as well as the second order systems. Am I correct? Any doubts in that? Any doubts in that? So this is our reference point. Let's say 1. Okay. So basically, what are the objectives? Why we wanted to go for feedback control or closed loop system? Okay. These are the objectives. We want our system to reach this reference value of 1 very fast. That means that we wanted to reduce our rise time. Is that clear? That is first. Okay. So we want our settling time also less. We want our system to settle the final value very fast. Okay. Settling time also should be less. And we want our system final response should not deviate much from the reference value of 1. That means that our final steady state error should be as less as possible. Also, we want our system should not overshoot from the reference value. That means this height should be as less as possible. That MP as less as possible. Okay. Rise time, settling time, steady state error, overshoot. Okay. So we want as less as possible values. Is this clear? Any queries? These are our main objectives: to decrease the rise time, to decrease settling time, to make the steady state error to 0, and reduce the overshoot. Okay. So this robustness we will deal in the concept called frequency response that will come in after week 7 or week 8. Is this clear? The objectives are clear. So for these objectives, we wanted to design this feedback control. Okay. So let's go step by step. Okay. So in the feedback control, we'll be having the different types. Okay. So basically, we will go with proportional controller, integral controller, derivative controller. So combinations: proportional integral controller, proportional derivative controller. Okay. So all put together, PID. Okay. Basically, if you start learning, okay, if you start learning, these are the controls. Controller. So if you start learning one by one, instead of going directly to PI or PD, so if you learn these 3 basic controllers properly, the rest will be easy. Okay. So in this session, what I will do is I'll handle only this proportional controller, all the derivations, etc. then you can do easily the integral and derivative controller, or otherwise we can see it in the next slide. Okay, let's start with that. So our aim is to design this proportional controller. Okay, first. Okay, basically, why do we need feedback controller? Okay, why you wanted to do that? Okay, let us start with this missile autopilot system, missile transfer function, GC of S, G of S, K by 1 plus tau S. Okay, so let us say tau is the some constant, system constant. Okay, and we wanted to give a step input. We wanted to give a step input. Okay, R of S is equal to 1 by S. Okay, let us say you started with the open loop system. Okay, open loop system, you have this plant. So the R of S we want to 1 by S. It means R of S is equal to 1 by S means what? R of S is equal to 1 by S means what? Your R of S is one value, unit step. You want your output Y. This is the, you want your output Y to reach this 1. Okay, so it means that this will be your R of t, this will be your Y of t. Your reference input is 1. Okay, you want your output Y of S to reach that reference value 1. That is our main aim. Okay, now in this, what is your Y of S is equivalent to? Y of S equal to what? R of S multiplied G of S. Am I correct? R of S multiplied G of S. Okay, let us say that in output is Y1 of S. Output is Y1 of S, which is nothing but G of S, R of S. You're multiplying the G of S, multiplying with R of S. Okay, so then divide that into the partial fractions. Okay, once you have that, if you take the inverse Laplace transform, you get this Y1 of t. Is there any doubt in this? From here, you are taking the inverse Laplace. You got this. Okay. So how this response looks like? Can anyone tell me how this response looks like? It looks like exponential only, correct? It looks like this blue curve only. Okay, so the blue curve. Okay, so here what you can see, okay, the system is slightly slower, slightly sluggish. Okay, the response is slightly slower, or you can say sluggish. Okay, now what we can do is, instead of R of S is equal to 1 by S, okay, let us say R of S is equal to 2 by S. R of S is equal to 2 by S. If you follow the same thing, let us say that is Y2, you got this response. Okay, now if you plot both Y1 and Y2, you can see here Y1 is this, Y2 is this. Okay, Y1 will settle to K value, Y2 will settle to 2K value. Correct? Y2 will settle to 2K value. Okay, so at 2, time t is equal to infinity. So one major observation what you can see here is, okay, one major observation, particularly if you see this line. Okay, what this line says, the Y compared to Y1, okay, Y2 reaches K value very faster. K value very faster. Am I correct? Compared to Y1, Y2 reaches K value very faster. Correct? Okay. So now the idea is like, we want our output to reach the value of 1 very fast. That is our main intention. Correct? As I said, this is our main intention. Our output, the blue curve, has to reach the red line, one line, has to reach very as fast as possible. If it is reaching as fast as possible, the discussed rise time will reduce, settling time reduces. Once it reaches, steady time goes to 0. And if it reaches very fast, the overshoot also gets reduced. Okay. So here, so the idea is that, okay, when we make 2K, it's rising very fast. The idea is, can we apply initially input very high value? Okay. After it reaches very close to the K value, we will reduce it. Can we do this? Right? This is the basic idea here. Okay. So why don't we apply high input initially so that system responds quickly and then decrease the input later. System responds quickly and then we will decrease the input. So basically, this can be done using this structure, feedback controller. Okay. So what we wanted to do is, initially we wanted to give high input, later we wanted to reduce. How it can be done with this? Okay. So let's say initially you are giving R of S, a high value of 1. Okay. Initially output is 0. Initially output is 0. Initially output is 0. This value is 1. Okay. So now you are taking the feedback. Okay. So you are taking plus minus. What is the value you will get here? 1 minus 0. That will be equal to 1. That input you are giving to the this K of S controller. Then controller will produce some control input U here. That you will give it to the G of S. Then it will produce the next output. Let us say that value is some 0.1. Okay. Next again you will compare. Okay. 1 minus 0.1. So that will be 0.9. Again you will produce UI. The next it will get, let's say, 0.3. Okay. So in this way what happened? Initially the value will be higher. Okay. So later as we go forward, the error is reducing. This is the error. That error you are applying to the controller. Okay. In this way, initially you are giving more output, then later you are reducing because error is reducing. Is this clear? This is the motivation for feedback control. This is what exactly the feedback controller does. Okay. Any doubt? Any doubt? Any doubt here?
Sir, how is it getting to like 0.1 minus only?
No, no. I just took the example.
Yeah, how can I get the exact whatever the thing here?
No,
How
no.
much percentage
Once you
it is decreasing?
no.
Like,
Once you know this G of S and K of S expressions,
yeah. Hmm.
okay. So let us say initially your system G of S, your output Y of S, you want it to equal to 1. Okay. So initially you're not applying anything. Okay. Here UI is 0, initial value. Okay. So you're taking the output here, this side, you're comparing both, you got a error of this much.
Yes, sir.
Okay. So that error you are giving it to the controller. Okay. Here K of S. What K of S does is it modifies this error and produces the proportional input. Okay. Produces the proportional input. Initially, previously that is 0. Now it produces some non-zero value. That input you will give it to the G of S. It produces now the new output, say 0.1 or some other value, which will not be a 0. Okay, this process continues. Okay, this process continues till your Y of S will reach 1. After reaching 1, it will stay there only. Okay, so this is the
Okay, sir.
motivation for the feedback control. Okay, now for the feedback control, this is the closed loop transfer function. Okay, closed loop transfer function. Now, important step. Is this clear, everyone? Till this point, the motivation for feedback. Now, from here, we are going for this proportional controller. Okay, so the proportional controller basically means the controller controller transfer function K of S, choosing the expression for that. So when we choose K of S is equal to K1, some constant, which is a DC gain, we call that is as the proportional controller, which is just a value. Okay. Now, so we substitute K of S is equal to K1. G of S, we have already considered this K by 1 plus tau S. Okay. Substitute K of S is equal to K1 and G of S is this expression, both in this closed loop transfer function. K of S and G of S. That is nothing but the GC of S. Finally, you have this expression. Okay. In this expression, see that K is system constant, tau is also system constant, both comes from G of S, whereas K1 is the controller gain. Okay. This value you can choose based upon your requirement. Okay. So now you can see. So once GC of S is nothing but what? Y of S by R of S. Am I correct? What is Y of S? Y of S is nothing but GC of S multiplied R of S. Okay. So now let us say R of S is 1 by S. Okay. So R of S 1 by S. This is the expression for G of S, GC of S. Okay. Substitute them and divide into partial fractions. Divide into partial fractions. Okay. Once after applying the partial fractions, okay. So apply inverse Laplace. Apply inverse Laplace. So finally, you are getting this expression, time domain, as y of t. Okay. So in this particularly, this tau c, okay, tau c is tau by k1, k1k plus 1. Okay, we call that is as the time constant of the closed loop system. Okay, here what is the observation? The K1 is the proportional gain. Okay, K1 is in the denominator. Okay, if you properly choose K1, you can vary the tau C. You can vary the tau C. If you choose more value of K1, tau C will be lesser value. Right? Tau C is less means what? Basically, tau C is nothing but what? Time constant. It decides how fast or how slow your response is. Right? So that means what? This is your output y of t. Okay. This will be another output. Okay. This will be another output. So this will be another output. This will be another output. These are different values of tau c. Okay. You can see that this is reaching after a long time. This one is reaching the steady state value fastly. Clear? So that is how this tau c plays major role. So we call the time constant of the closed loop system. Okay. You can change tau c if you simply change the value of K1. Is that clear? So what is K1 here? K1 is
Sir,
nothing but your, yeah.
in the graph, how can I assume the tau c is that line in that line only? Please tell me again. I didn't understand.
No. Let me draw it again. So here, this is your expression. Okay.
Yes, sir.
So in this, so this is time, this is y of t. Okay. So in this is the value you wanted to reach, 1. Okay. So now let us say the K1 is equal to some 2 initially. You will get tau C1. Okay. Let us say the tau C1 you will substitute here. You draw the response. Let us say that response is something like this. Okay. This is for tau C1. Okay. Next, take K1 is equal to 3. So tau C2. Okay. So you might get response something like this. Okay. As you increase the value of K1, what happened to the tau C?
It
Reduces,
will,
correct?
yes.
because it is inversely proportional. So you'll
Inverse.
get something like this. So time is less means the response reaches to the steady state value faster. Okay. This flexibility you're getting, you have the flexibility of choosing K1. By properly choosing K1, okay, you can change the response fastness. Response fastness is changing means what? Now you can see here previously what is your rise time. The rise time is this one, initial curve. But the final curve, what is the rise time? This is your rise time. See how much price time got reduced? Yeah, yeah. So it is like this. Okay.
Okay, sir.
So you can see here. Okay. So this is what the thing is. But the problem here is, okay, the major problem, you wanted to reach this one. Correct? You wanted to reach this one. Okay. But look at this expression. So suppose if I choose K1 is equal to 2. Okay. Say K is equal to 1. Okay. So if I choose K1 is equal to 2, what is that expression value is?
2/3.
2 multiplied 1 by 2 multiplied 1 plus 1. So 2 by 3 is it equal to 1?
No.
No. Okay, if I choose K1 is equal to 4, what is the value? 4 multiplied 1 by 4 multiplied 1 plus 1. 4 by 5. Correct? Is it equal to 1? No. Correct? So ultimately what? 4 by 5 is always less than 1. 2 by 3 is always less than 1. So it means what? Your y of t will not settle to 1, but it will settle to some other value less than 1. Correct?
Hmm.
Always you will have this difference. Even if you go to time till infinity. Is this clear?
Yes, sir.
So what is this difference called in our language? What is this difference? That is called as the steady state error.
Steady state.
Steady state error. Correct? So this is called as the proportional controller. So simply what we are doing, so that K of S, we are choosing the value of K1. Okay, then we are following the entire derivation. Finally, we are trying to plotting it. Right? What this plot says, okay, for any value of K1 you choose, okay, the response goes almost near to 1. Almost near to 1, but it will not reach to 1. It will not reach to 1. Okay, always you will have some steady state error. So proportional controller basically what it does, in conclusion, can anyone tell me? So it makes the system to act faster, correct? It's quickly going to, by properly choosing K1, what will happen from this image? You will choose the TC, tau C, correct? You will choose the tau C, am I correct?
Yes, sir.
By choosing tau C, you can change the system fastness, am I correct?
Yes,
You can
sir.
change the value of the rise time, correct? Yes, you can change the value of the settling time also. But only the issue is that, okay, it cannot directly go and settle to value 1, but it will go very fastly there, very near. It will go to the nearest value very fast. Okay, for example, it will go to 0.8 very fast, correct?
Yes, sir.
But it will not reach to 1.
Sir, here we are considering here the for the unit step thing.
Yes, yes, yes,
That's why
yes.
it's 1. If for any step is like 2 or 3, it would be like
No, it will be also same thing. Even if you consider that is a 3 value, so the response goes to 2.9 or 2.8. Still that steady state error will be there. Okay. So the proportional controller, what it does, it will help It will help the system to act faster, but it introduces steady state error. Clear? It
Yes, sir.
introduces steady state error. Okay. So advantage with the proportional controller is it will make the system to act faster. Disadvantage is it will introduce the steady state error. Clear? Any doubts? Okay, so this is major point. Okay, let us see quickly. Okay, for first order system. First order means you are taking GC of S as the one pole. Okay, so if you take GC of S as one pole and E of S is just K value, this is GC of S. Okay, so you are getting K bar. K bar is nothing but what? K by K plus 1. K by K plus 1. You can see the response, right? So previously you have calculated all these expressions. Okay, if you go back and see the week 4, you have calculated what is time constant, rise time expression, settling time expression for first order system and second order also. Okay, now with these, okay, so without controller, just a simple open loop, so you have these values. Okay, now with closed loop and controller K. Okay, controller K. So what happened here with open loop, the gain is 1. With the closed loop, the gain is what? K by K plus 1, which is always less than 1. Correct? That is
Yes,
first.
sir.
Second, time constant is tau. Here, time constant, you can change the time constant by properly choosing the value of K. Okay. Then, rise time is previously that is 2.2 tau. Now, rise time is tau by K plus 1. Suppose if we choose the K as the 2, what will happen? If K as 2, what is this value? 2.22 multiplied 0.5 tau. Am I correct?
Yes, sir.
Sorry. If
And
we choose the K is
0.33.
equal to 1. Yeah.
0.33.
Yeah, K is equal to 1. So that will be 0.5 tau. So the rise time, the time constant got reduced by half. Okay. Settling time also reduced. Clear? So there is a considerable improvement in the terms of rise time and settling time. Okay. So that is the first thing. You can consider the second order system also. Okay. Now your plant is this. Okay. You'll have one pole at 0, another pole at S is equal to minus 1 by tau. So same thing, this is your controller K, proportional controller only. Okay. So now if you do the same thing, okay, same process. So this is your closed loop transfer function. Okay. This is your characteristic equation. So once you make that characteristic equation to 0, you will get these poles. Okay. In this, okay. So if you choose your K value as greater than 1 by tau. Okay, if you choose your K value as greater than 1 by tau, okay, so you can change the pole's location. You can change the pole's location. In general, in the fourth week, you have seen this is the expression for second order system. Okay, omega n square by s square plus 2 zeta omega n s plus omega n square. Okay, so if you substitute, this will be your general system. You have K bar, zeta bar, and omega n bar. Okay, K bar is your crucial thing, right? So K bar, you can choose the value of K. If you choose the value of K, you can change the response of the system. Okay, so for the same second order system, okay, so with open loop, these are the values: rise time, settling time, etc. For the closed loop system with this controller, okay, so it is slightly reducing. It will not reach to 1, but it is reaches to some other value, K by K plus 1. Okay, natural frequency increases. So damping ratio decreases. Okay, the rise time decreasing, overshoot increasing, settling time there is no change. Okay, so ultimately, what is the proportional controller is doing? Okay, so it makes the system faster to reach the closer value. Okay, it reduces the settling time. Okay, so literally it is not giving much advantage in the sorry, it reduces the rise time, not giving much advantage in the settling time. Okay, so it increasing the overshoot. Okay, it increasing the overshoot, and ultimately it introduces the steady state error. Steady state error. Okay, that is one point. Second point is overshoot also increasing. Okay, so these are uh, disadvantages. So advantage is this faster, reaching to the closer value very fast. Clear? So ultimately what we are doing here, so we have this system, we have this closed loop system. This will be given to you. This you are choosing as K, proportional gain. Find y of t expression. Once you have that y of t, okay, find the rise time, settling time, etc. by using all the analysis you have done in your week 4. Then compare the values with open loop and closed loop. Okay. Next, this is with proportional controller. Okay. Next, what we do is derivative controller. So replace that K with S term. Okay. In the integral controller, replace that K with 1 by S. Do the same analysis. Okay. So basically this integral controller, it will remove that steady state error introduced by the proportional controller. Clear? The derivative controller, it handles that overshoot. It reduces the overshoot introduced by both this integral as well as the proportional controller. Is this clear? So that thing we will see it in the next lives. Okay. If there are any doubts, you can ask me. So I'll share this material also. You can check it.
Sir,